Hello, this is John at Electric Utility Design Tools. This video is a demonstration of our electrostatic contact current and field profiles tool. The purpose of this software is to help engineers quickly calculate electrostatic contact currents, electric and magnetic fields, audible noise, and radio interference for overhead AC lines. I'll briefly explain electrostatic contact currents and then we'll jump into the demonstration. Illustrated on screen is a common design situation for overhead lines. The situation arises when a metallic object that is insulated from ground is within the influence of the electric field of the overhead line. In this case, we show a large vehicle insulated from ground by rubber tires. If a person who is standing on the ground touches the object, they become a path for electrostatically induced currents to ground. The situation can be represented with an equivalent circuit. On the left, an AC voltage source represents the overhead line. A capacitance represents the electrostatic coupling between the overhead line conductors and the vehicle. And another capacitance models the coupling between the vehicle and ground. The person then becomes a parallel path to ground for the current in the circuit. Here we list two industry documents that provide limits for the electrostatic contact current. The limits are listed in terms of short circuit currents. This means that the person in our model is replaced with a short circuit to ground. The National Electrical Safety Code lists 5 milliamps as an upper limit. This is sometimes referred to as the 5 milliamp rule. The ICN IRP lists 1 milliamp as an occupational exposure limit and 0.5 milliamps for general public exposure. These documents provide additional conditions associated with these limits, which are important to review for any given project. The general objective then is to adjust the design parameters of the overhead line so that these limits are met. In today's example, we'll answer the question, what is the electrostatically induced contact current? We'll also show how to generate and view results for electric and magnetic fields, audible noise, and radio interference. The case study is that of a 500 kV transmission line in a 150-foot right-of-way. As shown on screen, we have information about maximum operating voltage, power flow, and current. We also have phase conductor and shield wire geometry. Finally, we have information about the largest anticipated object under the line, together with constraints regarding its position. The software is capable of modeling more complex corridors with multiple transmission and distribution lines, but this simple example will suffice for demonstrating project workflow and the intuitive nature of the program interface. Next, we'll start the software and begin the example. Okay, after starting the program, begin by clicking File, then New. This will open a new project. I'll first save this as something other than the default name. Note that more than one project can be opened at a time. These will show up as different tabs at the top, and you can click back and forth between the tabs as needed. This is convenient for comparing cases. On the left we have 4 tabs. They are Overhead Lines, Object, Input Validation, and Field Profiles. Each of these corresponds to a different aspect of the program workflow. We'll start in the Overhead Lines tab, where we enter information about the transmission or distribution line in the corridor. To the right of these tabs is a list of all of the elements that we will add to the corridor. At the bottom of the screen is the panel that contains input fields for whatever element is selected in the list. The main window shows a cross-sectional view of the corridor. The controls below that window allow the user to zoom in or out and to toggle visibility of the corridor element list or the input data panel. The user can also toggle visibility of the grid squares and can also change the size of the grid squares. Here I'll change them to 10 feet by 10 feet. At this point I'll also mention that the user can key in Control T to toggle the units between metric and English units. Toggling the units can take place at any time, whether you're entering data or reviewing results. Unit toggle can also be accessed from the View menu at the top. I'll leave this in English units while we enter the data. Next I'll click Zoom Extents, and you can see that we have here the edges of the right-of-way labeled. In the center is a vertical dashed line that corresponds to the baseline. This is the reference point from which the right-of-way edges and the plot extents are measured. I'm going to change the plot extents to minus 150 and 150. And this is simply for convenience in getting as much of the corridor in the view window as possible. The problem statement indicated that the right-of-way was 150 feet wide, so I'll change this to minus 75 and plus 75. At this point, we're ready to start entering the transmission data. Right-click on right-of-way and add new structure. In the lower panel, we can change the horizontal position of that structure within the right-of-way. We'll leave this at the default of 0, since the problem statement indicated that the structure was centered in the right-of-way. Now right-click on Structure and select New Circuit. I'll select Circuit 1, and we can see that the options include 1-phase, 2-phase, and 3-phase circuits. We'll leave this as the default 3-phase, and then if you want, you can enter information in the description. Next, select phase conductors. Here I'll reset the zoom. Notice the blue circles at the bottom of the screen. These indicate the position of the conductors or the conductor bundles. As we update the geometry, these will move around within the corridor window, and that gives us a quick way to visually verify that the information that we've entered is consistent. So we'll start by entering conductors per bundle, which is 3. We'll leave the default bundle spacing, 18 inches. Conductor diameter was 1.165 inches, and the phase conductor sag is 30 feet. The user has the option to enter unbalanced voltages either in magnitude or in angle. Our problem statement indicates balanced, so we'll enter the data as 317.53, which is line to ground kilovolts in RMS. That corresponds to 550 kV line to line. Paste that into all 3 phases, and we'll leave the default angle values of 0, minus 120, and 120. Next, the currents were 2,310 amps. And again, we'll leave magnitudes and angles to give a balanced 3-phase circuit. Horizontal position was plus and minus 30 feet, and vertical position 70 feet. Now if I zoom in on one of these blue circles, I'm using Control and scroll wheel on the mouse, you can see that the conductors are actually in there and they are to scale. The blue circle around them is simply so that we can see where they're at when we're zoomed out and can't see the individual conductors themselves. Next, we'll right-click on Circuit 1 and click New Shield Wire. And we'll enter that data, which was 0.5 inches for the diameter, 26 feet for sag, horizontal position of minus 24, and vertical position of 102. Now we had 2 shield wires, so I'll right-click on Shield Wire 1, select Copy, then right-click on Circuit 1 and click Paste. And then we'll go in and update the horizontal position to positive 24. At this point, we have all of the transmission line information entered. Now notice in the project name in the tab at the top, we have an asterisk. That indicates that we have unsaved changes. So I'll go in and save these real quick. And now we can move on to the next part of the project workflow. The Object tab is where the user can enter the object or vehicle to be placed under the transmission line for electrostatic contact current calculations. In our problem statement, we have specified that the largest vehicle is a semi-truck with tandem trailers, total length not to exceed 75 feet. I'll click on the Vehicles Semi-Trucks tab, and then we could work through the options to find the one that is the same size or just larger than the one specified in our problem statement. I'll click on this 28-foot twin trailer case here. Total length is 75 feet, so that's the one that we'll select. This is really all that's needed in the Object tab. I'll note here that we have about 40 different models. which are commonly used for this type of analysis. But if you have a case where the situation is unique and you need a model that is not included in the software, you can go to our website, to the Contact Us page, or you can email us, both of those are shown on screen, and request a quote to have a custom model added to the software. Next, we'll go to the Input Validation tab. This part of the workflow is actually optional, but it provides the users a quick opportunity to check for any inconsistencies in the data that they entered under the Object and Overhead Lines tab. To initiate the review, click Check, and then look for indications of warning or errors on the left. The program is comparing things like minimum conductor height to the height of the object that you've selected. It's looking for things that you might have entered outside the plot extents. Now we'll note that if there are warnings or errors, the program does not prevent the user from continuing on to analyze the geometry as entered. So the information here is just informational. It's not incorporated into the calculations. Next, we'll click on the Field Profiles tab. In this final tab, the user enters the computation settings and views the results. The computation settings are in this panel at the top left. For now, I'll leave those as defaults. You'll notice that the vehicle we selected is included in the corridor view window. This purple line indicates the center of the vehicle or object, and that becomes the basis or the reference point that corresponds to plot data later on. Behind the scenes, the program is using finite element analysis and charge simulation to generate results. And while the vehicle position on screen is arbitrary, behind the scenes the program is sweeping the vehicle through the corridor so that it can generate contact current results as a function of vehicle position. In the lower left, we have a compute button. When I select that, the program computes all of the results for all of the quantities: electrostatic contact currents, magnetic and electric fields, etc. Next to graph, there is a drop-down menu, and from this you can select the different quantities you want to view. I'll start by looking at electrostatic contact current, and I'll change the line width to 20 to make it easier to see on screen, and I'm going to hide the grid squares. A detailed discussion of electrostatic contact currents is beyond the scope of this presentation, but I'll point out that the program automatically calculates and displays on screen the results corresponding to the right-of-way edges, and it also shows the maximum within the right-of-way. In this case, you can see that the maximum is 5.064 milliamps, which, if we were using the NESC rule, is just above the limit. Next, I'll select electric fields, magnetic fields, audible noise, and radio interference. Now, one thing to point out is you may have noticed that some of these results were in terms of feet. It's much more common to see these types of results in metric, so we can again hit Control T to toggle between different units. Let me go back to the electrostatic contact currents. Once we've computed results, the input data is grayed out. That includes in the first tabs for overhead lines, so we can't go in and change this information. If we want to go back and change an input and recompute results, click Clear, make the change, and then recompute the results. Here I'm going to change the object orientation to 90 degrees to place the object parallel with the transmission conductors. I'll recompute the results and again select electrostatic contact currents. Now you'll notice that the maximum value is now 7.255 milliamp, and that increase is expected. More of the surface area of the vehicle is now underneath the region of maximum electric field. Before concluding, I'll quickly point out that you can export the data. This includes an export of the image on screen using the PNG button, or you can export the plot data in tabular format using the CSV button. This concludes our demonstration today. If you have any additional questions about our software, please feel free to reach us at the contact information on screen. Thank you very much.